In this video, we will talk about Kuratowski's theorem. One of the main ideas is the notion of subdivision. Given an edge in a graph, you subdivide it by putting a new vertex in the middle of the edge and keeping the old connections. So that means you add a new vertex W and you make it adjacent to the endpoints of the original edge, and of course you remove that edge. So it's like you split an edge in two. So in general, we'll say that one graph H is a subdivision of another if you could obtain H from G by subdividing possibly more than once. So for instance, up here, this graph is a subdivision of the original graph. But of course, the point is you could go even further and subdivide a bunch more, possibly, and still get a subdivision. So we will say that a graph H is a topological minor of another graph if some subdivision of H is a subgraph of G. So for instance, the triangle is a topological minor of this graph because it is possible to subdivide the edges. Let's see, like right here, and then map that to this cycle. Okay, it looks like I need at least one more. And there you have it. So that's what it means to be a topological minor. It's a generalization of the concept of subgraph that we need. So one thing that connects this notion to planarity is the following. If you have a planar graph, then any topological minor of that planar graph must also be planar. So for instance, suppose this was my graph G, and H here is my topological minor, so this means it's a subdivision of a subgraph of G. Notice that the subgraph of G has to also be planar, and subdividing edges doesn't change planarity because we're putting the new vertices where the original drawing of the edge was. And what's important is the contrapositive. If G has a non-planar topological minor, then G is not planar to begin with. So this gives you one way to prove something is not planar, is to give me a topological minor that's not planar. And Kuratowski's theorem is a strong result in that direction. Suppose we have a graph, then that graph is planar if and only if it does not contain the following two graphs as a topological minor, K33 or K5. As we've noted before, these two graphs are not planar. The strong theorem is, as soon as these are not minors of your original graph, your graph must be planar. In the future, to make this wording of the proof go quicker, we're just going to use the phrase Kuratowski subgraph to refer to any subdivision of these two. So these are our forbidden subgraphs for the notion of being planar. To demonstrate the usefulness of this theorem, let's look at the Peterson graph. So the way we usually draw it, it's clear it's not planar, but there's always the question, is it possible to draw it so that it is planar? And here we do see that we actually have a topological minor. So I have labeled certain vertices in red and certain vertices in blue, and I've deleted these edges marked in red. And the point is, from this red vertex, you can take this path to the blue vertex. For this red vertex, you can take this path to this blue vertex, and these already have paths to this other third blue vertex, and you start to see that you have K33 in here as a topological minor, and therefore the Peterson graph is not planar. So for the rest of this video, I'm going to talk about some preliminary facts about graph drawing that we're going to use in our proof of Kuratowski's theorem. Neither one of these are going to be rigorously proven because rigorously proving theorems about planarity is actually a bit challenging. But the first fact is that if you have a planar graph that's two connected, then every face of your graph is bounded by a cycle. So remember, when you have planar graphs, you have faces. When you have a tree, there's only one outer face, and it's not a cycle. This tells you that faces are bounded in the way you would have expected before we started this theory. And so how do we prove this result? Well, two connected graphs have ear decompositions. So take an ear decomposition of your graph. The base case, you only have a cycle. P1 is a cycle. Clearly, there's exactly two faces in that drawing, and both of them are bounded by the entire graph. All right, so suppose your ear decomposition has more ears than one. So that's the induction hypothesis. Take F to be a face of your drawing in some drawing of your graph G. And then what are we going to do? We're going to take the union of everything but the last ear. This is a subgraph of G. And so the point is we have a drawing of our graph G. We have this face. It's possible that part of the boundary of the face includes our last path in our ear decomposition. So if we remove that path, we have our graph H, and the point is F must be contained in some face of H, in this case this larger one. By induction hypothesis, since H is two connected, F prime is bounded by a cycle. So in this case it's this larger red cycle right here. And so we have two cases. The first case is this drawing was drawn poorly and this blue path is not part of F at all. So F is equal to F prime. In that case, there's nothing to show because we still have the same boundary. So the interesting case is when F is not equal to F prime, so exactly what we have pictured. Then this means that F must be contained in the boundary of F prime. Okay, let me state this carefully. The boundary of F must be contained in the boundary of F prime, which was the cycle C, union PK, this last path. So then we have what is sometimes referred to as a theta graph. And the point is, no matter how I drew this theta graph, F must be one of these three regions. And all three of them are bounded by a cycle. And so we're done. The last fact we need about graph drawing is actually a bit more interesting. Given any planar graph G and your favorite vertex or edge, it is possible to draw the graph so that your favorite vertex or edge is on the outer face. So this is a bit more unusual because this relies on some facts from projective geometry and stereographic projection. So what do? Take your original drawing of your planar graph G, highlight your favorite edge or vertex. What I'm going to do is take a sphere, a circle centered at the origin, and then work in three-dimensional space and look at this sphere. And the point is, from the North Pole, I'm going to take any point in the plane and draw the line from the North Pole to that point. It has to intersect my sphere at a unique intersection point. So for each point in my graph, drawing of my graph, I'm going to draw on this balloon, so to speak. And so then the idea is take your, in the drawing of this balloon, it's worth pointing out that the outer face is the region on the balloon that contains your North Pole. And so then I've got my drawing on my balloon with my favorite North Pole. Now I just move the balloon and rotate it so that my favorite edge, the region containing my favorite edge or vertex, includes my North Pole. And then I reverse the drawing. So then from this new North Pole, I draw through these points to the plane and draw the intersection point. I end up with a new plane drawing. This is somewhat vague, but it turns out this idea works. It's worth pointing out that because I'm doing this drawing's not accurate. When you do this process, the straight lines can become curved in general. So just pretend these are curved. But the point is you can always draw your favorite edge or vertex on the outer face. For those interested, you could go look up about homogeneous coordinates. This is actually kind of interesting and is the math behind computer graphics. It's a similar story.